Hello, and welcome to part 3 of topic number 8. Houston, hopefully we don't have a problem, getting up from and back to Earth. In the first video, we talked about launch vehicles, i.e. getting out of Earth's gravity well, how we go about it, the staging, the performance estimation. In the second video, we talked about orbital transfers, the Hohmann transfer, the fast tangent transfer, the bielliptic transfer, patch conics for interplanetary transfers, and then we finished up with talking about the delta V required for the lowest energy transfer to get from Earth orbit to the moon and to get from Earth orbit to Mars. Today, we're going to talk about getting back down onto the surface. So before we start, let's review our questions. Again, in videos 1, we talked about how do rockets work. In video 2, we talked about moving from one orbit to the next, and which takes more energy, more delta V going to the moon or Mars. And then today, we're going to talk about getting back out, that energy back out, or entry and re-entry. Key thing, how do you slow down? You have two basic options, though one of them is limited only to celestial bodies with a meaningful atmosphere. You can use a rocket, just like we did when we landed on the moon, and just like we do when we try to land on an asteroid, something without a meaningful atmosphere. You basically have to take out exactly the same amount of delta V that you put in. Now, the nice thing is very often our satellite is or spacecraft is much lighter coming back than going out because we've burned a lot of fuel to go out. So you don't need as much thrust and fuel, but you basically have to undo what you've done. The other option is to use the atmosphere, i.e. aerobraking. Now, the challenge here is that you don't burn up. Don't pull a Columbia. And then you have to realize that drag alone, just from the spacecraft, won't slow you down. So not burning up, you can see on the bottom of this Gemini capsule, the remains of the heat shield. It was an ablative heat shield that slowed it down. And then we'd have parachutes. The parachutes fail, you get this outcome. This was a Comet sample return mission that the parachute failed to deploy properly and crashed and broke open in the Utah desert. That's what you don't want to happen, especially if you have humans on board. Okay, slowing down. The way we do that is we generate a lot of drag through shock waves. Here is a typical semiconical blunt body capsule, like an Apollo type capsule. Here's our shock. It's a detached shock. And the reason we like detached shocks is they produce a lot of drag, but they also displace the highest heat loading away from the body. That saves us. If we do it, say, for the Millennium Falcon, we can see lots of shock waves. Now, these are attached shocks in many cases. This would indicate very high heat loading in those areas, which would, of course, cause structural failure. Or maybe a cat. Now, all of these images were taken in our HSST tunnel here at the University of Manchester. If you talk to Dr. Quinn, he will gladly talk to you at length about the beauty of this tunnel. These were done by a former PhD student who's now working for BAE Systems in Wharton. And in addition to the cat, we did a duck and a bee and other things in the tunnel. Here's our duck. And then this video is of the Millennium Falcon. So as you can see, all of these shock waves are forming off, and you get interactions of shock waves on other parts of the body, and all of those would cause increased heating and likelihood of breakup. That disintegration we saw with Columbia, for instance. Okay, so that brings us to the end of our quick introduction to getting back down. As a wrap up, in this topic, in the 3 videos, we talked about introducing rockets and launch vehicles, the rocket equation and staging, and that was video 1. In video 2, we introduced basic orbit transfers, the Hohmann transfer, where we move from a circular to elliptical or one elliptical to another, and then back to another final orbit. We did 2 burn transfers, which is this classic Hohmann. We did a fast tangent transfer and the bielliptic as another option. We talked very briefly about interplanetary transfers and getting from Earth to the moon and Earth to Mars, and the concept of patch conics, which you won't have to do in any detail, you just need to be familiar with. And then we talked about reentry and the issue with shock waves and all of those, and showed you some nice videos. The nice thing about those last bits is it's really the type of information that you should know. You don't need to be calculating anything at this point. It's just laying the groundwork for future activities in fluids, in hypersonics and high temperature gas dynamics, in space systems and the like. So that brings us to the end of topic number 8. In topic number 9, we're going to talk about propulsion systems. So I hope to see you then.